So in the last class, we were discussing that what would be the probability of finding the particle, finding the particle in the interval minus a to a, provided we are having this kind of wave function. We are having potential Vx is equals to minus of V naught Dirac of x. So we came to a point, and I told you that the wave function for wave function corresponding to a particle bound in such a potential is given by a e की power minus k modulus of x. So before finding the probability of finding the particle, before answering this question, that what will be the probability of finding the particle in the range minus a to a, we must first normalize this and find the this wave function and find the normalization constant a. In order to do that, I would simply take psi star psi x dx. This entire integral should be equals to 1. This entire integral should be equals to 1, since the probability of finding the particles somewhere in the space should be equivalent to 1. So simply minus infinite to infinite, you will get psi star psi. So you can write, I think psi was, so this is like a modulus ka square, and you have e की power minus 2k x modulus is equals to. Okay, further as I go, I can simply integrate it from minus infinity to 0 in a one way, and from 0 to infinity another. So in minus infinity to 0, you know that your wave function is given by e की power kx, and from 0 to infinity your wave function is given by e की power minus kx. So you have a ka square e की power minus kx dx here, and you have a ka square, you can take modulus as well, overall okay. This will be e की power 2kx, sorry. Is that clear? And so if it is the case, then integral would be equals to a square 1 upon 2k. Integration of e की power 2kx would be e की power 2kx upon 2k. So 2k comes, 1 by 2k comes here. E की power 2kx, place 0 here. So this will be 1. Place minus infinity, this will be 0. Plus 1 upon 2k. This entire thing is equals to 1. That implies a mod ka square is equals to k. It implies a mod is equal to root over k. So their normalization constant is nothing but root over k. Is that clear? So your normalization constant is root over k. So now probability of finding the particle in the range minus a to a would be equals to a e की power minus k x, minus k into modulus of x into, this will be a star. This is like the real part is only here, so you don't have to worry about it. Minus k modulus of x. So this will result in writing minus a to plus a. This will result in writing from minus a to plus a square e की power minus 2k x modulus dx. Is that clear? Now, what you can simply do is, you can simply integrate it. And what would be the answer to this? So you have modulus, you have to write the modulus. So basically from minus a to 0, your function is a square e की power minus 2, sorry, this would be plus integral from 0 to a, your function would be a, integrand would be a square minus 2kx dx. And this entire thing, and this a square you already know, your a square is k, so I can replace it by k, so I have k here. Integral of e की power 2kx from minus a to 0 would be e की power of 2kx divided by 2k from minus a to 0, and this will be e की power minus 2kx divided by minus 2k, so I'll write 2k, and this will be 0 to k. Overall, this will become k, and here you have 1 by 2k, so I'll write 2k outside. This is 1 minus e की power minus 2ka plus 1 minus e की power minus 2k. So overall, just take 2 common out. So overall, you will get the probability of finding the particle from x equals to minus a to x equals to plus a. It can be written as 1 minus e की power minus 2k. Further, you also know that your k is related to your energy, that is 2m E modulus upon h ket square. And your E modulus was given by mv naught ka square upon 2h ket ka square. So if you remember if you remember that your modulus of E is mv naught square upon 2h ket square, so I can write my k, sorry, this was root over. I can write my k as root over 2m upon h ket square, and then instead of modulus of E, I can write m v naught square upon 2h ket square. So this h ket is, so this will be overall 2 gets cancelled, and you have m square v naught square upon h ket ki power 4 root over. So this is m v naught upon h ket ka whole square. So this is your k. So overall, the probability of finding the particle in the range from minus a to a depends upon the depth of the potential. So basically depends upon V naught. However, the word depth would be not right here to say, because see, in any case, the depth would be very infinitely large, but the amplitude of, you can say, the term V naught. I mean, the potential is given by V naught minus V naught Dirac of x naught. So basically, I'm referring V naught to as the amplitude which is associated with the Dirac delta function. So overall, I would write my probability of finding the particle from minus a to a, and that will come around as, I think, 1 minus e की power minus 2 m v naught upon h ket square, and I think this is a. This is what I will write. So this is my probability of finding the particle in the range from minus a to plus a. That is 1 minus e की power minus 2 m v naught a upon h ket square. Now, another question that may arise is if there is a sudden expansion. So for example, if my potential is changed suddenly from, if my potential V naught, you can say potential amplitude, you can say potential amplitude V naught changes suddenly from V naught to V, say let's say 1, then the probability may change, because see, you can see that your probability depends upon this V. So probability will change. Probability will change, or you can say probability of finding the particle, the probability of finding the particle in the new bound state, in the new potential, sorry, in the new potential value, you can say, or you new Dirac potential, you can say, would change, certainly change. We want to find what is that change in the probability. We want to find what is the change in that, what is the change in the probability. So let's say if my final state is V1 and my initial state is V0. So let us first find what is psi of x. So psi of x is given by root over k e की power minus 2m V0 a upon h ket square. So let's say this is your initial wave function, and now final wave function, and this k is equals to, I think, m V0 upon h ket square. Now, if my psi final is given by because let's say my amplitude changes to V1, now my k would change, and that would become let's say it will become, let's say, root over k1. I will write k1 here as m V1 upon h ket square e की power minus 2m V1 upon h ket square, and then this will be a. I think this is clear. Now, and this will be modulus also, this will be modulus also, and I think a will no longer appear here. It's my mistake, because basically wave function is given by root over k e की power minus k modulus of x, and k is given by I think somewhere k I have written here mv naught, sorry, so not even 2 would be there, not even 2. So k is given by minus mv naught upon h ket square. So sorry for the mistake. This is minus mv naught upon h ket square. Okay, sorry, minus mv naught upon h cat ka square modulus of x minus mv naught h cat ka square modulus of x will be here, and here it will be minus mv1 upon h cat ka square. Now, what is the probability? What is the probability of finding the particle in the final ground state if initial ground state is psi I, final ground state is psi f? This is given by this expression, or you can write in integral version psi f star psi I dx modulus. So let us first find this integral I, and then we'll square it off. So let us first find this integral I. So what would this integral be? This integral I can be written as minus infinite to plus infinite. This is root over k, so I'll write root over k here. This is e की power minus mv naught upon h cat square modulus of x into root over k e की power minus mv1 upon h cat ka square modulus of x dx. And we can also do it from minus a to minus infinity to 0 and 0 to infinity. We can break it into two parts, but we saw initially also that they were actually becoming twice only. So why it was becoming twice, we can use a formula, we can use a property of definite integral, which suggests that if your function is even, this particular integral reduces to this particular integral. So since modulus function is an even function, so it hardly matters. So what I would do, I would simply take 2, and this will be, I think this is 1, I think. This will be root over k into k1, and this will be 0 to infinite. This will be e की power minus, I think if I'm not wrong, I will write minus mv naught plus v1 upon h cat ka square. And since 0 to infinite is there, so you can write modulus of x is simply x dx. Okay, is that clear to you? So overall, this becomes it. I will write it as 2 times root over k into k1. And then I have this integral, which gives me, I think if you integrate it, you will get h cat square upon m v naught plus v1. Because at infinity, this particular thing will become 0. And at 0, it will become 1. And this negative will get absorbed. You can find it on your own. So I'm leaving that particular thing for you. Now your k is given by, I will again write mv naught upon h cat square, and your k1 is given by mv1 upon h cat square. So your overall thing I can write here as this m gets cancelled, h cat square gets cancelled, because this will give you h cat square, this will give you h cat square at the denominator, overall to be h cat power 4. So you cancel them up, and you ultimately find this integral I as 2 times, I think it will be root over v naught v1 upon v naught plus v1. And what will be the probability? Since probability of finding the particle in the new sort of potential, if it can be written as modulus of I ka whole square. So overall, this will be squared. So what is the probability of finding the particle? You can say in the new state. I mean, you can say in the new potential. Okay, what is the probability that we find the particle in the new sort of potential? That will be I mod ka whole square. And that probability is given by 4 times, I think, v naught into v1 upon v naught plus v1 plus square. So just as an illustration, what if my potential is reduced to half? So now my potential is reduced to half, that is v1 becomes v naught by 2. Then what is the probability of finding the particle in the bound state in the new potential? That would be 4 v naught into v naught by 2 divided by v naught plus v naught by 2 whole square. And you can simply find this will be, I think, 8 over 9. So if you just find this will be 3 by 2, the 3 by 2 is 9 by 4. There is a 2 here, so this will be 8 by 9. So probability of finding the particle in the new potential, in the region where you're in the new potential, when you're like when the strength of the potential is reduced to half, is 8 over 9. That is, in percentage wise, the probability that the particle remains bound in the new potential is around 89%. If potential is halved, the probability of finding the particle remains in the bound state is 89%. Why I'm saying bound state? Because you understand this entire thing we were saying for e less than 0, and the entire derivation also, we saw that for an attractive Dirac delta potential, there is only one bound state possible. So if the strength of potential is halved, then the probability of finding the particle in the bound state reduces to 89%. Okay. Similarly, if it is quadrupled, so for example, now your final potential is 4 times V naught. So overall, this probability will give you 4 into V naught ka square divided by 5 ka whole square V naught ka square. So this gets cancelled. This will be around 16 by 25, isn't it? So overall probability in terms of percentage wise, it will reduce to 64%. So probability of finding the particle in the new in the bound state, provided the strength of potential is quadrupled, is around 64%. So this is where we are summing up our lecture that we've done on the attractive Dirac delta potential. Just to recapitulate, we were discussing an attractive Dirac delta potential given by minus V naught Dirac of x. Okay. We found that there will be only one bound state given by mv naught ka square upon 2h ket ka square. If I'm not wrong, mv naught upon h ket ka mv naught square upon 2h ket ka square. Since energy is negative, so I would write only one bound state is possible. What will be the probability of finding the particle from minus a to a? It will be e to the power minus 2ka multiplied by like this will be this particular thing I have written as m v naught upon h ket ka square. Overall, we found this, and then we found that what are the changes. We found that what are the changes in the probability provided your potential varies. That is, if potential suddenly becomes V naught by 2 or possibly V naught by 4, how to find what is the change in the probability of finding the particle in the new grounds in the bound state. So how would the probability change? So these were the questions. This was the central theme of these two lectures. Now we are discussing one-dimensional potentials, and in one-dimensional potential, we are restricting ourselves to Dirac delta function, Dirac delta potential. So in the next lecture, we are going to see how the wave function would vary if instead of writing an attractive Dirac delta potential at x equal to 0, if we change to, let's say, x equals to a or some different variations that we'll do as we go along. Till then, take care.